Hello everyone. Today I'm going to discuss fluid pressure on plane and curved surfaces. So I'll be deriving first the formulas and the subsequent principles. So let's begin. Let's consider the uh, surface, general shape of surface that is in contact with fluid. So let's have here a body of fluid. Let's just assume that only one side of the surface of this body is in contact with the liquid. And this is the projection of the area. And the pressure variation, we know that it increases with depth. So this is the centroid of area, CG. Then the total pressure or the center of pressure. The total pressure acts at the center of pressure, which is also defined as the centroid of the pressure diagram. So this is the projected centroid of the area. This is the area, and this is where the line of action of the total pressure or the hydrostatic force acts on the plane surface. So that's the center of pressure, and the distance between CG and CP is denoted by E. Then we draw a line along the plane of the area until it intersects with the liquid surface. Let's call that S, point S. And the angle that this area makes with horizontal as theta. So that is also theta. And let's call this point 1 and the lower point as point 2. So the intensity of pressure at point 1, which is by Pascal's law perpendicular to the surface, is P1. And at point 2, which is deeper, so the intensity pressure is P sub 2. And let us assume that that's the pressure distribution or diagram. So since pressure is not uniform, we consider only a differential area, which is parallel to this line here, so that the pressure over that area, very small area, is constant from the previous principle. So the intensity of pressure is denoted by P, and this is the differential area over which this uniform pressure P acts. And the corresponding force also is denoted by differential force because the area is very small. And remember the principle earlier that considering a very small area, the pressure is the same as long as that every element of that differential area is equidistant from the liquid surface. So the distance of the centroid of this differential area to the point S along the plane of the area is denoted by Y. And of course, this distance is the vertical distance of the point, any point on this differential area to the liquid surface as H. And the force, the total pressure or the force acts through the center pressure Cp. So first, let's derive the formula general expression for F. We begin with this differential force, which is equal to intensity of pressure times dA. By the way, the distance of CG to the liquid surface S along the plane is denoted by barred Y, and the distance of CP along the plane to point S is Y sub CP. So the vertical distance of the centroid of area to the liquid surface is denoted by barred H. So the total area is A. So differential force is pressure times dA from the definition of pressure. So integrating F therefore is equal to pressure, where pressure is equal to gamma of this liquid times H, and differential area is just dA. Because gamma is constant, then we have, and replacing H by Y sine of theta, then factoring out, putting gamma and sine theta before the integral sign, then we have integral of df is f equals gamma sine theta integral of y dA. So the expression integral of y dA from calculus is actually the static moment of area. So this is simply equal to the moment of this differential area with respect to point S, axis S. So it is equal to area times barred y, also by Varignon's theorem. So from calculus, integral of y dA is area times barred y, or we interpret this in another way by Varignon's theorem that the moment of area about the line through point S is area times barred y is equal to the sum or the integral of the moment of sum of the moments of this differential area, which is dA times y, or y dA. So replacing integral of y dA by area barred y and rearranging, so we have gamma sine theta area barred y, or gamma barred y sine theta times A. Denote or noting that barred y from this right triangle here, we have a right triangle. The hypotenuse is barred y. The opposite to theta is barred h. So therefore, barred y sine theta is barred h. So we have F equals gamma barred h times area. So we use this formula whenever the surface area is in contact with one liquid and the liquid surface is exposed to the atmosphere, or the pressure is zero. But if you encounter a complicated situation, we have a liquid here, but there is pressure specified on top of the liquid surface, or this area is below layers of different liquids, so that would be a complicated situation. Then we interpret that gamma times barred h is pressure at the centroid of area, so that F is also pressure at the centroid of area times the area. So these are the two expressions for the total pressure, or the force, hydrostatic force F. One is for simpler situation, just like in this figure here, where the liquid surface is exposed to the atmosphere. And the other one is applicable to any situation, especially if the surface is under the liquid layers of different liquids, or the surface of the uppermost liquid is subjected to certain pressure. So by Varignon's theorem, to derive E and y sub Cp, the moment of F about axis through point S is equal to the sum of the moments of its components, dF times moment arm y. So F times y sub Cp equals summation of dF times y. The moment of one component is differential force times y. Replacing the summation notation by integral form, and dF by this expression here, dF is equal to gamma sine theta y dA, then y is simply y, and again putting gamma sine theta before the integral sign, so F y sub Cp equals gamma sine theta integral of y squared dA. Again, from integral calculus or from statics, this expression in integral of y squared dA, so that is integral of constant distance y squared times dA, is the moment of inertia of this area about line through point S. So integral of y squared dA is simply the moment of inertia of this area with respect to line S. So replacing that expression by, or F by gamma sine theta area barred y times y sub Cp, and we have gamma sine theta I sub S. By transfer formula, or before that, we can cancel gamma sine theta. So area barred y sub Cp equals I sub S. Now, we have transfer formula for moment of inertia of area from statics, and it is equal to the moment of inertia with respect to the centroidal axis plus area distance square. So it is I sub Cg plus area barred y square. So I sub S equals I sub CG plus area barred Y square. So therefore, uh, replacing IS by this expression, and after that we divide everything by area barred Y. So we have Y sub ZP equals I sub CG over area barred Y plus barred Y. And replacing further barred Y by barred H, barred Y is barred H. So we have this right triangle opposite to theta is barred H over sine of theta, replacing barred Y by barred H. So Y sub CP minus barred Y equals I sub CG over area barred Y, and barred Y is barred H over sine theta. So therefore, from the figure, the difference between Y sub CP and barred Y is E, the distance between CG and CP. So E therefore is I sub CG sine theta over area barred H. So this is the the formula, practical formula for eccentricity E, or the distance between the centroid of area and the center of pressure. Now, take note that theta is the angle that the plane of area makes with the horizontal. And of course, I sub CG would be the centroidal moment of inertia of area depending on the given area. So for vertical distance, if the plane area is vertical, then barred Y becomes barred H for that case, because theta would be 90 degrees for that case and sine 90 is 1. So it is I sub CG over area barred H. Now, let's have I sub CG. So this is for vertical surfaces, this is for inclined surfaces. Point 2, of course. So conditions for CG and CP to coincide. So what are the conditions for CG and CP to coincide? For CG and CP to coincide, the eccentricity E must be 0 in the formula, and I sub CG sine theta over area barred H will only be 0 if sine theta or theta is 0. So when the plane surface is horizontal or theta is 0, then eccentricity E will be 0 from the formula. The second condition is when the denominator, which is the formula, is I sub CG sine theta over area barred H. So if barred H is so high or so large, then E approaches 0. That means when the area is brought to a very, very deep point, then we can say that uh, CP and CG will coincide, or barred H approaches infinity for that case. And the third case is when that area is exposed to, of course, gas pressure, so that the intensity of pressure will be uniform. So these are the conditions for which CG and CP will coincide. Now, in most cases, CG is always above CP, in most cases, for when there is a value of theta. But there are situations, especially theoretical ones, where CP will be above CG, and that is when the surface of the liquid is subjected to a very high negative pressure compared to the depth. So that's the only case where CP will be above CG, but in most cases, practical situations, CP is always below CG along the plane of the area, a distance equal to E, and we already derived E. So for moment of inertia of common plane figures, so let's have a review. Let's make it fast because this is not the uh, situation or the time where we have to review them. You're supposed to know them already from integral calculus and from statics. So it's a waste of time if we're going to derive it. So I'll just present it here. Moment of inertia with respect to the centroid is bh cubed over 12, if you can remember, for a rectangle. And with respect to the base, bh cubed over 3. For triangle, with respect to the centroid, bh cubed over 36. The distance of the centroid from the base is h over 3. So bh cubed over 36, and with respect to the base, bh cubed over 12. For circles, with respect to the centroid, it is pi r4 over 4, or pi over 64 diameter to the fourth. So in fact, with respect to any axis through the center, it's the same. For semicircle, with respect to the centroid, we have 0.1098 r to the fourth, where the distance of the centroid is 4r over 3 pi, if you can remember. So with respect to the base is pi r fourth over 8. And with respect to the vertical axis to the centroid, it's the same because it's just like two quarter circles. About this axis, two quarter circles. About this axis, two quarter circles. So it is pi r4 over 8, or 1/4 or 1/2 of pi r4 over 4 for circle. Then if it is a quarter circle with respect to the centroid, so half of 0.1098 is 0.5499, 0.0549 rather, r to the fourth. With respect to the centroidal axis also, it's the same. So with respect to the radius, so it is 1/4 of pi r4 over 4, so pi r4 over 16. Iy equals I. Then for other cases, use the general formula. The strip should be parallel to the axis in question so that you can derive it as integral of constant distance square dA. So I'll just leave this to you to derive these formulas, especially the location of centroids. For ellipse, it is with respect to the centroidal axis, or along the major axis, it is pi over 4 AB cubed. Pi over 4 AB cubed. With respect to the minor axis, it is pi over 4 A cubed B. So, or BA cubed. Then if this is a quarter ellipse, so all you have to do is, with respect to the centroid, it is zero point 0, barred x is 4a over 3 pi, barred y is 4b over 3 pi. So I barred x is 0.0549 ab cubed, just like a circle. We just replace r by r, and r to the fourth by, let's break it into r and r cubed. So we replace one radius by a. So I barred y is 0.0549 a cubed b. So with respect to the x-axis, 1/4 of pi over 4, so pi over 16 ab cubed. With respect to the y-axis, pi over 16 a cubed b. So this is our barred y. It's the same, no? But that's for quarter ellipse. So the general transfer formula for moment of inertia is I with respect to any axis is equal to I barred x plus area barred y square, and Iy is I barred y plus area barred x square. For half parabola, so you just go over with the derivation here. This is a demonstration. So moment of inertia with respect to the x-axis is 2bh cubed over 7 from here. Then I barred x plus area of parabola 2/3 bh. Then the distance is 3h over 5. The distance between this centroid and the x-axis is 3/5. This is 3/5. This is the vertex of the parabola. It is open upward. So that's why I barred x is equal to 8 over 175 bh cubed. And I barred y Similarly, for I bar twice, Iy equals I bar y plus area of parabola. Then distance between uh, the value of bar x is 3/5 of 8. So this is 3/5 of 8. So that's why you'll get I bar y equals 19 over 480 b cube h. So that's it for. So this is the suggested strategic attack for the following cases. For this situation here where there is only one liquid and the surface is exposed to the atmosphere, you solve for F by specific weight barred H times area formula. So that's barred H, so gamma barred H area. And for this situation here where this is the gate, this is the surface, and we have two different liquids and we have a gas pressure here, then we use the pressure diagram instead. So F is pressure at the centroid times area, remember, formula. And the pressure at the centroid is equal to, uh, also equated to gamma or specific weight of liquid 2 because it is liquid 2 that is in contact with this liquid, with this surface, times barred H, so that you can solve for barred H. Now for F, because we have to use the pressure diagram, this is the magnified figure. So this is the pressure diagram due to, this is due to P. Then we have to add pressure here, which is gamma of liquid 1 times H1, if that's thickness is H1. So F1 is equal to the volume of this pressure diagram, and it is equal to area of the rectangle, which is pressure times the height of uh, this gate, times width perpendicular to the board if it is uniform, if the width perpendicular to the board is uniform. So we assume that this gate is, or this wall is rectangular. So pressure times H, that's the area of this pressure diagram rectangle, then times B, which is the width perpendicular to the board or perpendicular to this plane. So B is the width perpendicular to the board, and this is the pressure diagram. Due to the liquid, it is equal to P plus gamma of liquid 1 times H, and that is continued as a rectangle, so gamma 1 times H2. So because this is liquid 1 and the depth or thickness is H2, so the pressure at this interface is equal to P, pressure here, plus gamma of liquid 1 times H2. So the increased pressure here is gamma times H2 for this triangle because P is already here. And the force is called that F2. It is equal to the volume of this pressure diagram. So it is 1/2 of gamma 1 H2 times height H2, then times width perpendicular to the board B. So that you can easily locate its location. It is centroid of this triangle, which is 1/3 of H2 from this interface. Then F3, it is equal to this rectangular pressure diagram. It is just gamma 1 H2, height H3, then perpendicular to the board B. So F3 is gamma 1 H2 times height H3, area of the rectangle, times width perpendicular to the board B. So that is F3. And finally, due to this liquid 2 here, so the pressure at the bottom is equal to P plus gamma 1 H2 plus this intensity pressure gamma 2 H3. So that's gamma 2 H3. And the force is denoted by F4. F4 is equal to volume of this pressure diagram, which is area of triangle times width perpendicular to the board B. So it is 1/2 of gamma 2 H3 times H3 times B. And the total force therefore is equal to F1 plus F2 plus F3 plus F4. So in general, sum of F1 to Fn. So the line of action of the total force is located by Varignon's theorem. So it may be located from the bottom or from the top. So you just use Varignon's theorem. That is, total force F times, let's say from the bottom, by y bottom is equal to F1, then moment arm or centroid, distance of centroid of F1, or this rectangular area from the bottom, plus F2 times distance from the bottom, plus F3 times distance from the bottom, plus F4 times distance of F4 from the bottom, and so on and so forth. So that's it. So for the location of the center of pressure CP, when the plate is not symmetrical with respect to the vertical axis of plate, so for instance, this is the situation, but it is continuous. For example, the edges are continuous, that we can express the edges in terms of a single variable, or we can define it by an equation. So the distance of the centroid of this area is barred h, and this is the center of pressure, not necessarily along the vertical axis of symmetry because the area is not symmetrical. So there will be barred x, there will be E sub v and E sub h. So for E sub v, it is I sub cg sine theta over area barred h, the formula we developed earlier, where sine theta, if this is vertical, then sine theta is just 90, so that it becomes I sub cg over area barred h. Then for E sub h, then once we locate center of pressure vertically, after we solve E sub v, all you have to do is draw a line through the center of pressure. And remember that if the strip is horizontal, the pressure is the same on this horizontal surface, because remember the principle that the pressure is the same at all points on the same horizontal plane in a homogeneous fluid at rest, or the distance of the horizontal strip from the liquid surface is the same. So the pressure is constant. Knowing that the pressure is constant, it means that the pressure distribution is rectangular. So if it is rectangular, it means that the center of pressure is half of the length of the line through the center of pressure. So that is, if the length is L, then the center of pressure is L over 2 from the left or L over 2 from the right. So that's it. So when the area is symmetric with respect to the vertical axis through its centroid, then E sub v is I sub cg sine theta, or simply E, because sine theta is 90 for that case. And E sub h is, E sub h is simply L over 2 minus this distance here. So we can easily solve for EH. So compute E sub v first, then compute the horizontal EH. Compute the length of the horizontal line through center of pressure, say L. Then from there we can locate the center of pressure, so that we can evaluate E sub h. So that is. Now let's proceed to the principles on fluid pressure on curved surfaces. What if the surface is curved? So we have here case 1, liquid is above the curve. So like in this situation, so we always have to imagine that this is our body or our back, and if the liquid is above our back, so the force would be tending to push our back to the right, and for the vertical component, of course, it is downward. So this is the principle. All you have to do is draw lines through the ends of this curve, and the vertical projection of that curve, assuming that this curve is, the length of this curve is constant, perpendicular to the board, or perpendicular to this, the plane of the slides. So we will denote that by B, and the vertical projection of the height as H, and the length perpendicular to the board or perpendicular to the slide as B. Then for FH, we simply apply the same principle as that of plane surfaces. That is, FH is specific weight barred H area, where barred H is the distance of the centroid of this area, projected area from the liquid surface. So that is denoted by barred H, and center pressure is below, and the distance is E sub V, or simply E. Then FH is the same, gamma barred H area, or pressure at the centroid of this projected area upon the vertical plane times the area of this projected area of this curved surface. Then for the vertical, we draw vertical lines through the endpoints. Again, for a horizontal component, we draw horizontal line in order to define this height of this projected area of this curve, which appears to be a rectangle whenever the length perpendicular to this viewing direction is constant, which is equal to b. For the vertical component, we draw lines through A and B, the endpoints of this curve. And remember the principle that friction cannot develop when the fluid is at rest. So the fluid is at rest, or the liquid is at rest here, so no friction can develop. Therefore, the vertical component of pressure or force is simply the weight of the liquid above this curve up to the liquid surface. So Fv again is equal to the weight of this liquid above the curved surface. And it should pass through the centroid of this volume, because Fv is simply the weight up to the liquid surface. So therefore, the resultant force acts here, and you can compute the magnitude of this resultant force as square root of Fh squared plus Fv squared. And it makes an angle of theta, of course. So Fv is weight of liquid above curve AB. It is gamma times volume above curve AB. So case 2, the liquid is below the curve. So what if the liquid is below the curve and we still imagine that this is our back? So for the horizontal component, it's the same. It's now acting to the left, of course, because the projected area is still this rectangle here, and the centroid is there. So FH is equal to gamma barred H times area. It's the same. Now for the vertical component, of course, if we imagine that this is our back and the liquid is below our back, we feel that we are buoyed up or pushed upward. So therefore, this vertical component is equal to, so we still draw vertical lines through the endpoints of the curve up to the imaginary liquid surface. This time, the vertical component is upward, because if we imagine that this is our back, then we will feel that we are pushed upward, and that is equal to the weight of imaginary fluid bounded by the vertical lines through the endpoints of the curve up to the imaginary liquid surface. And of course, it is still passing through the centroid of this imaginary volume. And the only difference to this case here, Fv is now upward. That's the only difference. But it still passes through the centroid of this imaginary volume. So that's it. That's the principle. So Fv is weight of imaginary liquid above curve AB, and it is gamma times volume of real or imaginary liquid above curve AB. So when the curve is circular, of course, this resultant force passes through the centroid of the circular curve. Again, when the curve is circular, the resultant F passes through the center of the circle, or the center of the circular curve. So that is very important, and I want you to remember that. So that's all for this lesson 3, the principles. I hope you will not forget the formulas, and other important formulas would be you should recall the moment of inertia so that you can locate the center of pressure. Remember that the force is acting at the center of pressure, not at the centroid of the area. So remember that. And for the Force on plane surfaces, the force is always perpendicular to the plane surface. And for curved surfaces, we have to consider two components, FH and FV. FH is simply gamma barred H times area or pressure at the centroid of the projected area of the curve upon the vertical plane. And to do that, you have to draw a horizontal line through the endpoints of the curve in order to define this height of this rectangular projection and apply the formula for force, which is gamma barred H times area. For the vertical component, there are two situations. When the liquid is above the curve, so it is downward, and it is equal to the weight of liquid above this curve up to the liquid surface. For the other situation where the liquid is below or under the curve, then it is upward. But the formula is the same, although that in the second situation, we use gamma of liquid times the volume of this imaginary liquid. So that's the only distinctions. So I will end the lecture now.